Probably all like that. Putting the old chairs here.
Okay, meeting is announced open. So today's speaker is Geffrey teaching us about Janus quantum dots.
Well,
Again?
well, it's going to be mostly pretty pictures, and that's about it.
So he will be talking only about his research. It's not journal club presentation. It's just his data, whatever he was able to calculate for this topic.
Yeah. Okay. So, we have the Janus quantum dot die interactions. The three structures that I worked with, two were the quantum dots. Okay, this later is working. So,
It sometimes takes time, and then it's becoming brighter, and then in several minutes you will see it.
So first we have they're both quantum dots are lead, cadmium, selenium, with one being cadmium rich and the other one being lead rich. And then you can't see it because the thing is covering up. But this is the black dye. This is carboxylated bipyridines with thiocyanate with a ruthenium in the center. So, just some general observations. The cadmium rich is a lot more spherical than the lead rich, which that makes sense, given the nature of lead selenium and cadmium selenium. But you're not here for that. You're here for some
More complicated structures.
more complicated structures, yes. So here's the initial structures. I didn't label them, but the first three are the cadmium rich, and then the last three are the lead rich, and these are just, I put the dye on the quantum dot in three different configurations. We have one where I put it on the lead, one where I put it on the cadmium, and one where I put it on the interface of both. And
before you go, can you return back to your structures previous slide? This slide. So which surface? They both kind of cut in the same surface? Is it? Do you know the name for this surface? Or maybe Jabba can answer this question, because this is your structures.
Yeah,
Right? Both are your structures.
Yeah.
So like this kind of H is coming from 1, 1, 1,
1, 1, 1.
but you also have structures with 1, 0, 0. Right? Kind of
Yeah.
like this, cut it like that.
Yeah.
But what's the reason why you didn't give it to Ben to work on it?
So in mostly in literature they always suggested that it's supposed to be 1, 1, 1 surface.
And if you just look on the total energy, because let's say if you look on your 1, 1, 1 and 1, 0, 0 for lead enriched or cadmium enriched, right? It's exactly two separate.
And also
just total energy. Do you see difference in total energies between the structures? Which one is more stable? Which one is less?
I can look on the
Okay. But yeah, probably the first thing would be to compare the total energy, just to see which of these cuts, wherever the surface, and you probably have more than you have just two surfaces.
No, but problem is in this case 100 is symmetric in lead and cadmium.
It means you have just lead.
Yeah.
It's the same number as
And
cadmium.
cadmium, but in 1, 1 surface it cannot be symmetric in this case because 1, 1 surface either lead or cadmium is.
And why is it a problem? Oh,
is it because of conformation geometry? How is it?
But why we don't want to have the same number of lead and cadmium? What's the problem?
Okay, in that case we need to get, not a square cubic rock solid structure. We need to get the different structure. You need to put like more than 136 atom in that case.
When you have 1, 0, 0?
If we cut 1, 1, 1 surface, it's not possible to make a symmetric. Yes, because 1, 1 surface.
No, I understand that.
Yeah.
The
But
question
if you
is
wanna
not
make
this. You're saying that you're not using the case of the symmetric one when you have the same number of lead and same number of cadmiums with a facet 1, 0, 0. you're using this because in literature they see more like 111.
Yeah.
But my question is, we still can compare and see
But
which one is more
they have
stable.
different atoms, so
You have different number of atoms.
different number of different types of atoms.
So you cannot
yeah.
just look on the
You
total
cannot
energy,
just total
but you
atoms
can
and
calculate the surface energy, same as Naveen was calculating for
yeah.
the
Mm.
how it calls plates, nanoplates, right?
Did you look at the ionization energy?
Ionization energy is not useful.
But it's not.
What's the
it's
purpose of
big
it?
plus,
Ionization energy
yeah,
is just the
get
energy
ion.
needed to
No,
take out electrons. We're talking about
because it's not a
conformation, it's
molecule.
atoms, not electrons.
Yeah, so in machine learning, they take the gas phase molecule, atom, and they say, take the whole system of this, minus the gas phase of lead times however many lead you have, minus cadmium, times how many cadmium, minus selenium, selenium. Right, so you do a single point calculation on an isolated atom.
Oh, this is, I
But
guess,
in
what
this
we
case,
use when
yeah.
what we call surface energy.
Okay.
Yeah.
Then you take in kind of atoms as isolated one, as many as you have on the surface, and it's more complicated formula, yeah.
But in you can just ionization energy doesn't make any sense in this case because it's a big molecule, so they have a different facet. It can bond it in different sides. It will give you the different energy.
But I think he's not talking about ionization
Like,
energy.
yeah.
It's not ionization energy
Sure.
he's talking about.
Oh, okay.
So like if you take it and you blow it apart
Mm-hmm.
into infinitely separated atoms, what would be the well?
Yeah, if you separate atoms, then in that case, yeah.
Yes.
Okay, but the question about which surface to use for really, which surface is more preferential, right? Although we know that in experiments they see this, they might change the conditions and they might see a different structure, right? So this question still is open, and it's not
This
probably on
one,
your side,
yeah.
but on your side to address it.
In 110 is maybe an unfeasible site because in 101 surface is can be only selenium rich surface. So that means in one side selenium binding with the lead and other side selenium forming bond with cadmium. But in 100 surface there have a cadmium or cadmium and selenium both. So that means
You
you
still
need
will
to-
have one surface from this and one from another. You still can put,
But they have a forming a
Similar.
bond with the selenium, lead, cadmium or place.
so why not? Why you think it's not possible? We don't know, right? We don't have this data from experiment or from anything. We don't know what exactly happening there on a level of really creating bonds. So the only thing which we can compare is talk about the more preferential based on the thermodynamics conditions, right? Which one is kind of getting the least energy wherever we calculate it.
And what I have to see seen in the 100 surface is create a big, what's it called, a spherical shape in the empty, in a huge empty space in the middle of the
Cage,
yeah.
which again, interesting structure to look on.
Mm.
So I wouldn't just eliminate it just because in experiments they were so far not published anything on 111, because again, if the surface will provide, if the structure will provide more interesting properties, people will find a way. Change in temperature, change in conditions of their reactions, right? And then maybe, if they really put effort, it's probably they will be able to.
Yeah,
get
now
this
I'm doing
places.
some temperature ramping for that 100 surface structure one. Seems like it's take too long time, still temperature is too high. It's
Well,
just
anyway, so there's still open questions, but we
Yeah.
probably need to address it as well. Sorry for interruption, but yeah, this is not formal presentation, so you will be interrupted, not a big deal.
Whatever, it's all pretty pictures anyways. So, on to the optimization. The cadmium one had some issues and it's not really keeping up with in terms of optimization, but look at the cadmium rich ones. When you place the dye on the lead surface, in fact on both of the cadmium rich ones, the carboxylic groups really like to attach themselves to the quantum dye. In this case, there's a very severe bend, for
Bond,
the
you mean?
bend.
Back to heat.
Like it's
The molecule is
yeah,
kind of
the dye is
almost destroying.
yeah. And
But this is
sample-
vacuum. This is in vacuum, right?
Yeah, this is in vacuum.
If you put solvent, everything might be changed.
Yeah, so
And this is for the break
Yeah.
to calculate.
And have you looked on the tetrahedral shape of the molecule, central molecule? Is it banded or is it just reoriented to form a bond with the bolts? What is the bond dihedral angle at the center?
I haven't measured it.
That you can,
Right.
right? You're still
You
thinking
know.
that you need to have the octahedral structure,
Yeah.
right? In between these blue guys, the nitrogens.
Yeah.
They should kind of create this octahedral with a central atom of, with the center of this octahedral should be on a ruthenium, right? And I guess his question is whether these angles and distances really break this octahedral structure, means it's becoming not all ages are exactly the same as it's supposed to be in a perfect octahedral. Is it this way elongated or that way? Or maybe you even losing the planarity, maybe your four atoms not anymore in a same plane. They might do something kind of different angles, distortions, right?
Well, to be honest, I haven't looked at that.
But
So,
it's a very good point. You have to, and maybe create a table with this geometrical information for each of your structures.
question?
So I don't know anything about this stuff, but did you expect it to only interact with one interface, or could it interact with two, like it wanted to here?
Well, I put it on one, and I guess I kind of expected it just to stay that way. I didn't expect it to, do that, and as
You
well
mean
as
you start with one carboxylate group
Yeah.
attached, but then it's rotate, so to use both carboxylate groups.
yeah.
Can we go back to the image?
To finding the positive.
So it
physical
looks
side.
like
Could be.
the one, so the one on the right, the carboxylic group, is like in the plane of the interface. So it might be that there's a very, very highly electropositive region where the electronegative oxygens could help satisfy it, so that in that case it drops down and it really bows it. Where if you go on this other one where it's only on the lead, it might just rotate it down.
Yeah.
So it also
But-
might depend on where you put the one that's on the
But
left.
my understanding that in both cases he starts with only one group attached,
Yeah,
right?
so did you start with the one in the middle?
Yes, they're all
So
they're
these
all
are the
rotating.
initial structures,
He
and
tried
it
with a
correlates
different
to
conformation.
this one and that one.
But this is your initial, right?
Yes.
For those
These
which
are-
you're showing at the next slide.
Yes.
So you start with this and you end up the both carboxylates
Yes.
attaching.
So I have you also tried the one positive charge conformation. In that case, one CO you attached with hydrogen, right? In that case,
This-
you
no,
have
no, no.
that. This
Well,
one is both
but
of the hydrogen.
This is carboxylates.
Yeah.
But you're saying that he also tried
One-
with one proton on a one is
proton on the
protonated.
carbon.
Those are still optimizing. There was some weirdness going on there.
So in this case,
So,
whatever you place this carboxylic group, it always banded to the ender with the surface, right? Other one, both carboxylic group.
well, for the cadmium-rich ones, the lead-rich ones do something else. And in this case, the
This is
thiocyanate.
lead rich.
Oh,
Yes,
okay.
the lead-rich. In this case, the thiocyanates. It's interact with the quantum dot in all three cases. And I thought that was interesting. It could be,
But again, it might be interesting, but on the other hand, to be sure
Yeah.
which one is kind of more preferential, you need really kind of go back to the question of Braden and then Levi's kind of comment. You probably really need to start with both carboxylates on a already attaching to the surface as initial structure, and compare whether, and then see whether it stays like that and whether the energy would be even low, and maybe even try, looks like you already optimized it, so it probably stays in that way, and compare with the total energy of these structures. And then it will be clear whether it wants to go through sial, or sialate, or whatever it is, isocyanate, or it still would prefer to have both carboxylates. But if the carboxylate is too far away, then it's okay to have the isocyanate. But if you start already, that molecule will be aligned slightly differently,
Yeah.
then the lowest conformation would be with carboxylates rather than cyanates.
Yeah.
It's a good observation, but I think we need to do extra step to make the conclusion.
Yeah. I mean, I was gonna say that it could have been due to just the way that I oriented the dye on the quantum dot, but
So is it happening because of excess negative charge on the carboxylate group or because of the quantum surface?
Good
Because-
question.
Both carboxylate group are negatively charged, right?
Yeah.
Same as isocyanate.
Same as, yeah.
They also have negative charge in this.
Yeah, so that because of that negative charge tends to go on the surface of the quantum dot. And it's a vacuum, maybe that's also
No, but why not carboxylate? You still expect that your carboxylate should be more electronegative
By-
than sulfur, right?
Yeah, in this case, I don't know about sulfur, but in the solution, it can neutralize that charge or the attractions between the surface and carboxylate.
What you're trying to say, if you involve solvents, then
Solvent,
again,
yeah.
your attachment might
It
be
will be
different. You will
different.
have completely different story. Yeah, because you will screen out this very strong dielectric effect. And your charge will be not as strong anymore because with dielectric constant. And if it would be large dielectric constant. Yeah, so for sure we need solvent calculations, which
Yeah.
again, something in your list to do, right?
Yeah, it's on my list to do. I have like a few things on my list to do, but you know. So next is some fun animations.
So this is exactly how it happens, right?
Yes, this is.
And you
how-
comparing two cadmium enriched?
This is cadmium enriched where I put the dye on both, and then this is lead rich where I put the
Uh-huh.
dye on both, and you know, just a fun comparison. See how they optimize and.
No, choose the dihedral.
I mean, bipyridine and not octet is still okay.
Yeah, the octahedral is still.
Yeah.
This you can clearly see. Octahedral is probably preserved.
Yeah.
The molecule by itself, it just reorient. It's really a lot. How to say? It rotates around this carboxylate group.
Yeah.
Yeah.
It's not really changing the bands, bipyridines or anything.
It's still interesting that it really likes the interface between them.
This is not surprising,
Mhm.
and maybe Ben
I-
can explain it. Why it really prefers the interface. Why it looks like the interaction between when you really involve both different materials is more kind of beneficial. Any ideas why? I can help you with the word dipole,
Dipole. So,
and you think about dipole in both cases.
So
I mean, in both subsystems. Okay, another hint. What do you expect? Dipole on the surface, you just talk about completely pure lead selenium surface, or pure cad selenium surface, or when you have the interface?
So I suppose a pure surface would have a more even charge distribution.
And dipole
and,
moment?
uh,
If it's more pure distribution, more evenly distributed,
would it be like out of the surface? Or like
the direction you really need to get into more, how to say, technical things. But again, what is a dipole? What is the main requirement for to have the dipole moment? Formula maybe, if you remember.
I don't remember the formula, but I guess
Does it depend on the charge?
yes.
But what exactly with the charge?
Like charge over distance
Times distance.
times distance.
So it means the dipole increases if you separate your charges, if your plus and minus will be well splitted, but if they will be kind of at the same positions, then dipole would be smaller, right? So you really need kind of charge separation to have a very good dipole, to have a strong dipole, to have a high value for the dipole.
And I suppose that the interface
And
would provide that.
you probably can think about the electronegativity of cadmium versus lead. In both cases, you have seleniums. So, but you having different metals, cadmium and lead, looking on periodic table, you probably can assume which one is more electronegative. Can you? Well, cadmium is really higher in the periodic table comparing to lead.
So.
And the higher
I don't remember.
electronegativity goes across the across the periodic table.
So,
roughly, of course, there are some more detailed trends, but roughly speaking, it goes like that to the halogens. To the halogens are the largest at the top, right?
Oh, this way.
Yeah,
Okay.
from diagonal. Means it goes this from down to up and from right to left.
Left to right.
Oh, wherever it is, yeah. This way. I'm showing the right way, right?
So it goes from heavy alkalis to halogens. Okay.
So,
Roughly.
yeah.
Due to screening of the nuclei.
Well, yeah, you can, actually it's the general chemistry. We just learning this in general chemistry 2 weeks ago and had the exam yesterday. So I don't want really kind of to go to the really question in general chemistry problems, but just based on the ideas that you expect different electronegativity of cadmium and lead, and cadmium is more electronegative, not very much, but still a little bit. So this already makes kind of splitting between your plus and negative charges in a different way, and more splitted when you have different facets, when you have different materials, lead and cadmium, rather than when you just have a surface with just lead, or just lead and selenium, or just cadmium and selenium, right?
Yes.
So at the interface, you expect to have much bigger dipole moment,
Yeah.
rather than just on this surface or that surface. Although the dipole of cat selenite is higher than dipole of lead selenite. So they also have different dipole moments as again, because they have different metals contribution. But the interface where you really will have very, not even, like what you said, like not as even distribution of charges, right? You really will have, one goes, more negative will go to probably cadmium and more positive will be much more on the lead side. So this creates a very strong dipole. And what about your molecule? Is it a polar molecule?
Well, it's neutral, but it's polar.
Right. So again, you will have very strong dipole-dipole interaction. And of course, dipole will be reduced when they interact. And this rotation and this reorientation probably really helps to minimize the overall total dipole moments when both dipoles of the surface at the interface and dipole of total dipole coming through the molecule, right? They should kind of compensate each other and hopefully provide the least possible dipole at the final structure. And this probably dictates this reorientation of molecules that they want to go with both to the surface, right? Because when another one is going up, you kind of not probably compensating completely the dipole at the surface, since your dipole of molecule kind of is not as big if you reorient it this way. And yeah, same for sulfur, in this case for the isocyanates. So that's why it's not really a completely unexpected result. You probably can, even without any calculations, you could probably expect that the most favorable in terms of thermodynamics, lowest energy binding, probably should happen really somewhere at the interface rather than just on lead or just on cadmium. And hopefully we really will see, we can support this intuitive estimation based on your calculations with numbers of total energy, I don't know, binding energy and so on.
So, next slide is some partial DOSes. Again, the cadmium-rich cadmium isn't finished, but thing that I
So
noticed...
just a second, you have, this side is lead enriched or not?
Cadmium-rich is top.
Ah, okay. And not finished, just one structure is not
Yeah,
finished.
just that one's not finished. So a thing that's quite evident is all the band gaps are closed. And this concerned Jabed
And me.
and you, I suppose. And I didn't actually put it on here, but I actually calculated one of these structures. I think it's the lead-rich dion both in acetonitrile. I calculated one of the both ones in acetonitrile, and the band gap was still closed.
So solvent doesn't help to do anything with the band gap.
Yeah, I mean the dye was pushed, but the quantum dot still had states beyond the 0 point. So, and as kind of an illustration.
But do you have the dose of just the structure by itself of the Janus?
Yeah, I do have that one. So that was like 2.
So gap is open when you don't
2.3
have
and
that.
gap, yeah.
And again, it looks like, so black is your dye, right?
Yeah.
So it's really dye contributes, like the gap is closed on the dye? This is what it means?
Different.
Yeah, HOMO and HOMO -1 both are mainly on dye and also surface on.
Do we have then the dose
So-
of just dye?
Of just dye? I should have done that, I did.
We need it,
So,
just to be sure that your dye is having the right band gap. And again, it might be also very sensitive vacuum versus solvent.
and then, you know, just one thing, Jabed asked me to do this and help me get some molecular orbitals for this structure, the cadmium rich with dye on both. So we have HOMO -1, HOMO, LUMO, LUMO -1, and then band gap just to show. HOMO and LUMO, you'll find electrons on both the dye and quantum dot, which shouldn't be happening.
Is this LUMO?
It might
ratio?
happen. It's a charge transfer character, right? What?
Is this LUMO? I guess yesterday we saw that LUMO is, which one is now LUMO plus? I'm not sure. Is that
Looking at the
correct?
PDOS, it looks
Luma plus
like-
1, this is what you have deep to the right, right? Like the red
No, see,
guy,
this
which is
one
well
is
split.
I'm
Am I right?
Yeah.
confused about his
Luma plus
LUMO.
1 going from energies around wherever. Your units here is unclear what exactly it is. I guess it's probably 1 electron volt to the right.
Qualitatively agrees.
Should be.
Or you don't know. Or Luma plus 1 is still in this red reach near 0.
I don't.
You need energy first to see.
Yeah.
Are you talking about one state being really kind of closing this gap and another state is really far away from it? Or both are contributing to this small red peak near 0?
Ask the questions as many times as you want. I don't remember the answer.
My question to ask you, I mean, I'm asking this question, hoping that after you're done with your presentation, you come and write all my questions as least to do or whatever what you have to do when you return, when you return back to your work.
Does it? But if we look at the PDOS, is the red line lead?
The lead, the red line is
Lead, blue is cadmium, black
blue
is
is
dye.
cadmium, black is dye.
So if you look right around 0, right below 0 is predominantly dye,
Yes.
some lead, which matches what you have for the bottom two. And then if you go above the gap or whatever, then it's predominantly lead and some dye.
Yeah.
So then those also look somewhat similar. So yeah, it's hard to tell if both of those are in the first peak, or if it's not. If you don't use a normalized Gaussian, if you just use the normal Gaussian, it would appear that the height of that peak is 2. So then it would mean that both of those are in that peak.
So you just need to know the energy of the state
That too.
to answer this question the easiest way. Okay, but it would be nice to know where each orbital contributes to this plot.
Any other questions? Because this is the last slide.
Oh, this is the last one.
So yeah.
So you're not showing your.
Oh, then let's go in a second circle.
So you you don't have your solvent dose. You said like you check, but you don't have.
I have one,
figures yet.
but I made it immediately after I submitted this, and I only had the one. So, but the gap was closed again. So.
Yeah. So first of all, we need to calculate the dye, and since you're doing vacuum calculations, you also have to calculate your dye in a vacuum
Red is dye.
to see what happens with the dose. And as I said, like previously, we saw really very bad behavior of the dose for the dye in vacuum, because we have this artificial charge transfer state, and when you put solvent, the polar media, then this artificial charge transfer state gone, disappears, and then your gap is opening. But it might be really the effect of interaction as well, right? So but that's why if we look on a dye, and if dye not really doing bad things, either in solvent, and we need to look at both in solvent and the vacuum, right? First. Second is you need to do I suggest to do calculations of dye, optimized dye, and just taking exactly the structure as you have from, just cut the quantum dot and have the structure preserved, not the optimal one, but preserved as it is when it was attached to the dye. Because some conformation, which still probably happens due to the surface, might also affect this change in a gap of the dye or something, right? So there are three things which can contribute. One is just really artificial effects, which really due to the calculations, and this is of course we need to be sure that then it's not having any physics or chemistry in it, and we need to be sure that this is not the case. It's a bad thing, right? Hopefully it's not our case, but you need to confirm it. Second, this effect might be due to the very strong distortion on the geometry of the dye, and again comparing optimized versus this geometry by itself without surface, right, can answer the question how much this really contribute. Actually four. Second, and again do it in a solvent and vacuum. Second, said the interaction, that maybe this effect is really coming due to the interaction, and not interacting dye and not interacting quantum dot, Janus quantum dot, have open gap, but due to the interaction the peaks are shifting and so on. And of course, if it's due to the interaction, then solvent, how, like you say, it's not opening, but maybe it's shifting a little bit, or at least we need to know how much the solvent will contribute as well. Right? So, fourth is kind of solvent, but we need to include solvent in each of these three.
So I have a question somewhat related. If this closed gap is due to the disorder or conformational change of the ligand, is it experimentally feasible for the dye to kick out multiple ligands and have a large surface, like take up a large amount of surface on the quantum dot? Or is the ligands that are on the quantum dot when they're synthesized, would that prevent it from doing this? And if it is, then could you remedy this by putting a single layer of ligands around it, which then it won't let it coordinate to the surface?
You have done it, or at least I was asking you to do it, and I think you started calculations with ligands, right?
I haven't gotten anything yet.
But we
so-
discussed it, right?
Yeah, we did discuss it.
So putting ligands, of course, putting ligands on the leads or cadmiums and cadmiums probably will prevent this bending. Also putting proton to one of the carboxylate groups also will definitely not allow this, will kind of minimize this effect as well. Although we still will probably have cyanides to contribute. And also starting optimization. When you say you were looking on a dose with solvent, have you just take these structures and recalculate the dose in solvent, or have you recalculate and re-optimize the structure in solvent?
I will admit I just put this structure.
Oh, okay. See, it's also, yes, it's probably really it definitely not coming just from the electronic structure due to this, maybe against this artificial charge transfer states, which you will be immediately eliminate. If it was this problem, putting solvent should really kind of eliminate this. However, if this state's coming due to the conformational things, and in solvent, this conformation might be different, right? So looks like optimization and solvent is still needed to do as well. So it's actually number 5 probably. Not just put solvent and see the effect of solvent on the electronic structure, but we really need to re-optimize, maybe not all, but maybe at least a few, re-optimize it in the solvent to see whether change in the conformation in solvent might be very dramatic, having very dramatic effect on the electronic structure, dramatic in a way that it opens. Nice, but very, very interesting thing that two isolated systems supposed to have open gap and somehow we get in the closed gap. Can you return back to comparison of your doors for different configurations, right? Like here we have again the very left to right, whatever it is. This is right? So this is left. The very left case. This is where you have attached to LED, and the top one also LED.
Yes, top is also LED.
Mm-hmm. And then the last one, which I cannot see because of this image.
The gap is also closed.
I understand, but can we see any other interesting features appearing just due to the position, not just opening, closing, but maybe some other smaller kind of features, or they all look very much, not very much different? Like comparing your two bottom ones, I would say they're probably not very much different, right?
The most interesting things are around the gap or lack of gap. I mean, there's a few like additional states for lead.
But I would say if you compare cadmium enriched versus lead enriched when both are attached to lead, right? Here your ligand state is definitely kind of more separated from the quantum dot, while in your lead, and again you didn't show the orbitals for cadmium enriched case, you're showing only orbitals for lead enriched, right?
The molecular orbitals were for this case.
Oh, for cadmium enriched, but for that case.
Yes.
Okay. But my point is that maybe this charge transfer localization may be also different. And if you look on the luma, which is well separated, I mean the conduction band well separated from zero, right? They also have kind of red, like on the top, your red is well distinct from blue and black, while in the bottom one they kind of overlap, right? So like these small features maybe also make sense to take a close look again, drawing orbitals and seeing. So they're not exactly identical, right? And these features might be also interesting to investigate.
Yeah.
So if we look at the lead rich and the left and the center, even though you put the dye on cadmium, there are still states that are right at the band gap for lead.
Yeah.
So did any of the dye go to the lead, or is it only on the cadmium side? Because that's kind of strange that you would have localization on the other side of the quantum dot.
No, one side is bonded with dye and lead.
This would be the two that you're talking about, and
Okay, so it's not on
the
the
dye
lead
didn't
side.
go to the lead.
So it's
No, first one is the lead, right?
yeah.
Yes.
So there's the lead and then cadmium.
Both are lead and
So-
both are cadmium or the interface.
Yeah, it's just strange that you would have like a trapped state or a defect state both on the lead, even though it's not passivating the lead side.
No. Can you go back to your dose?
Yeah, I'm trying. There you go.
You're saying that in all cases, even if it's cadmium enriched, you have red kind of in your occupied states.
We can't really say cadmium enriched
because
we
not
don't have the
finished one.
yeah.
Yeah.
But if we look at only lead rich on the left and center, at the
Which
Which
two?
one is it?
the
These two?
yeah, those two, not the one that's covered up, both have lead at the homolumo.
Well, the problem is I cannot really differentiate between blue and black in this case, so can I?
Yeah, so if you look at the cadmium, the blue is the one that goes up. The black is the one that's.
But do we have orbitals for this case on your slides or not?
No.
So we have only for one structure.
Yeah, only for one.
Okay. Yeah, but again, those will not give you exactly the information where the orbital is. We need to look on the orbitals to be sure that, because it's probably hybridized states, of course. It's not just coming from lead or just from cadmium. Also, if it's on the surface, you're saying why it's hybridized with cadmium. Because it's probably not as, it might be. Can you return back to your orbitals again?
For the regular structure without any ligands, do you have a quasi-type 2?
So like Luma 1, it looks like, is it sitting just on the cadmium side? Am I right?
Like,
I look on the total.
I oriented it in a weird way so that I can't.
It looks like your lead is kind of on the top, right? It's looking on this figure, it looks like you have to have much smaller portion of lead, right? And lead is kind of on the top right, I would say. And this guy sitting on a left bottom. And left bottom should be mainly cadmium. So it looks like your Luma +1 should come from cadmium rather than lead, but your DOS not showing it. You don't see any blue around this. This is actually the answer to your question. Something is in contradiction. If you look on the Luma +1, it's really coming from cad side rather than lead side.
No, they have a lead side too.
it looks like it's
It
around
might be, but
that.
just a little bit,
Presentation is
right?
not-
No,
Mainly it's coming from cadmium.
The d orbitals are centered around a black atom.
Black, yeah.
Yeah.
So that's lead.
Yeah, that's the lead.
Yeah, his presentation is not, I mean,
Yeah, I
image is
didn't-
not
I didn't orient it in a very
Oriented, yeah.
friendly manner.
But just look on the very bottom part. There is no lead at all at the very bottom, and there are the bubbles there. There is? Really?
Yeah, it's cut like that, I think.
This is lead. That's lead.
Oh, this is lead.
Lead.
Yeah.
Lead.
Oh, so you
Image
face
is showing
lead
from
surface to us.
100
Yeah,
surface,
it's-
that's why, yeah. Is 11100.
I wasn't really paying attention to how I oriented it when I took these screenshots. So.
And this might be also kind of the answer to the question why the gap is closed. I'm pretty sure that you probably have this state not appearing in a gap for your pristine Janus quantum dot. So we need isolated structures also kind of to compare one by one and looking on the orbitals. So maybe the interaction really pushing the orbital kind of to this, although it should be, I agree, it should interact like you expect that the near the gap orbitals should come from where they interact, right? If they interact on lead, they should come from lead, but if they interact on cadmium, they should come from cadmium. But looks like in this case, they're all coming mainly from lead.
This one is.
But on the other hand, if you compare, well, but you 100% sure that the gap is open in the bare door? Same methodology. No, you're showing me VASC.
No, no,
It's not
this one is
VASC.
Gaussian.
Same, what function by the way?
PBU1.
Yeah,
And
this
yours is
PBU1,
also
yeah.
PBE1? Gap is open, but we don't know which one is which one. We need projected.
Yeah.
So it might be that due to the type 2 nature of the electronic structure, that any
Type 2?
Yeah, but
Ah.
this one, yeah,
But
this
this
one is
should be-
type 2.
It should be seen here.
Yeah,
this is not PDOS.
No, I
But
do
gap
have
is open.
PDOS, but
Yes, but my question was, why is lead always at the
Yeah,
gap?
so it looks like this state is
Versus-
moving probably to the gap somehow.
Yeah, so whatever you put on it, it moves both of the lead together, and then it kills the gap.
It might be the reason, but the question is why.
Yeah.
Because intuitively you not expect that this should happen. Okay, so you put really many interesting questions with your calculations.
And I have no answer.
It's good because it's not the finished project yet.
maybe because
So it's just showing you how much information you still can dig out doing this kind of things, right? So it's definitely not even done, probably 10% only done, right?
Yeah.
So,
Any other questions?
Can you show the fun videos
You want
again?
to charge
The fun videos.
Fun videos.
I like the
We
fun
need
videos.
music. We need music for this.
quantum dot is
These are GIFs actually, so.
I still can put like additional music just playing on the other screen.
You just didn't want me to put the fun videos.
No, I have a legitimate question. So if you look at the left one, at the beginning of the video, it blows up right away. Did you optimize this before doing it, adding stuff to it?
I was given the. I'm shifting blame. I got the optimized structures from Jabed.
Is it blowing up or is
That always
it moving?
impacts.
Looks like it's blowing up and all.
It might be just the angle, and it's just looks like it's blowing up, but it's actually just.
But definitely the interaction with this sulfur atom, right? Acting on a cadmium, and also it's kind of acting on this nearest selenium. Of course, they changed the alignment as it was initially, when there were no interaction with sulfur.
But the whole thing seems to blow up.
Yeah,
I
so
feel like
it-
the whole.
When you take it from bulk,
It just rotates.
it-
No, it just rotates.
No,
It's not
it's
really
not
changing
ball.
the structure by itself.
No, it seems like it's blowing
No,
up a little
it-
bit.
yeah.
So every time
And
I've
it was
optimized it,
optimized, but it shouldn't
goes
be.
I
blowing
don't
up.
This wasn't
see any-
optimized with
I
Gaussian
don't
beforehand.
This
Probably.
No, left side, left
it
one.
could be, but even when I have
Ah.
optimized
Can you
structure,
just slow down
typically
this
only,
one?
like,
Yeah,
Uh,
it's
these-
very, but again, this is huge dipole. This is a very polar molecule. We calculated the dipole of something more than 100 device for these molecules. So it's a huge, and for the cat selenium is around 20 for lead surface dipole, and for lead it's something 5 or 10, I don't remember divide. So it's a huge dipole, and when you interact with the surface, you drastically change the interaction and the dipole. That's why you're not really, I mean, it's very natural to expect that even the atoms which are far away from the binding side should feel this and maybe rearrange, because you're really changing the dipole of the entire system. But good catch, I thought it just rotates. I didn't really kind of pay attention that it's changing a little bit the structure of bonds. I mean, bonds kind of becoming longer a little bit. Yeah, now I can see it. Nice.
It optimized.
and then you put it out.
Yeah, he put the dial.
Yeah.
Any other questions? Should we go one by one? Which, what do you think? My students were already asking a lot of questions. Are you satisfied with the performance of your students?
Absolutely. You know,
Okay, then let's
to
applaud. Yeah. I don't have money. Yep. And with Sunnybow, the problem you now cannot really predict whether you get the support, and even if you get it, was what, $500? How much?
Oh, once you get it once, you can't get it
I
again.
understand, but what was your award?
I think 500.
And your award was?
I didn't have money for my award.
Oh, you didn't have any money. Wow.
But if anyone would consider today, they have a deadline for early registration and reduced fees.
November
30th.
today.
Today.
You need to register today?
Register today and abstract by the last day of December.
For the, is it $100 off?
Yep.
So it means